All right, so we're going to get into different kinds of mechanisms, simple machines, things like that. There's 6 of them. We'll look at 3 of them today. Um, Keep in mind that you can always pause, rewind, rewatch this as many times as you need to. So I'm going to actually go pretty fast, but don't freak out. Go through this at whatever pace you need. So of the 6, we're going to look at these first 3. What we define a simple machine as is a mechanism that manipulates magnitude of force and distance. Magnitude just means how much. A number, 10 pounds. 6 simple machines, lever, wheel, and axle, pulley, and then later we're going to look at inclined planes, wedges, and screws. The big thing that we're trying to get out of this is it's called mechanical advantage. It's a way to either get more or less force or more or less distance. So to get it, it's either the ratio of the magnitude, that's just number again, number in a unit, of the resistance and effort forces, or the ratio of the distance traveled by the effort and the resistance force. And whatever you do, ratio is just this over that. You take that divided by that and you get a number, a calculated ratio. So that tells you how much you are changing something, either speed, force, distance, function. So if we look at these boxes, one is going up the ramp on the long way, one is going straight up. The blue arrow represents the force of the box going down, or what we would consider weight. The red arrow is the force that we have to apply to make that box move. I would just call it an applied force. So a mechanical advantage of 4-to-1 tells us what about a mechanism? Well, as far as how much force we have to put on it, the effort force is 4 times less than the resistance force. So since the box going the long ways up the ramp is going 4 times farther distance, that red arrow should be 4 times smaller, or 1/4 of the magnitude of that red arrow. The red arrow on the box going straight up. To get that, you have to give something up. So to reduce the force, you have to increase the distance. So we could look at it that to go the long ways up the ramp, you have to go 4 times farther than if you were to just pick the box straight up. The way we define work in this class in engineering is different than what we probably think of as work in our daily lives. If we want to do work in the engineering sense, you have to apply a force to an object, move it a distance, and that distance has to be parallel to the force. So the force applied on an object times or multiplied by the distance traveled by that object parallel to the force. It has to be in that same direction. So we've got our initial position of this yellow box, this object. This arrow is a force going to the right. That means we're pushing it to the right. Here's where it's going to start. Here's where it's going to finish. We've got this parallel distance. And look at that, it slides. So work is the force applied, the magnitude of that arrow, number in unit, times the distance it traveled, parallel distance it traveled, parallel to this arrow. So product, that's multiplying, the product of the effort times the distance traveled will be the same regardless of the system's mechanical advantage. That's that ratio. And knowing how we compare these ratios to 1 lets us know something. So we're always going to compare to 1. If our MA, and that's just mechanical advantage, if it's greater than 1, then you're going to be using less force. So proportionally, less effort force is required to overcome the resistance force. You don't have to push as hard. What you give up is distance. So if MA is greater than 1, you have to go a greater distance. Proportionally greater effort distance is required to overcome the resistance force. If that mechanical advantage is less than 1, then you have to push harder. You have to have greater force. A proportionally greater effort force is required to overcome the resistance force. But what you gain is you don't have to push it nearly as far. Proportionally less effort distance is required to overcome the resistance force. Mechanical advantage, this ratio that we would get, is never going to be 0, or it's never going to be less than 0. You're not going to have a negative mechanical advantage. We're going to look at 2 ways you can calculate mechanical advantage. One is ideal, while we'll get to the other one, I guess. But ideal is if everything was perfect. This is what it should be on paper, in a perfect magical world. So in theory, this is your math. That would have to be a situation where there's no friction, which is no situation. But we can try to reduce friction and use this as an estimate to get pretty close. So we are not going to consider friction. It's all about the distances, the ratio of the distance traveled by the effort and resistance force. The resistance force is like the weight of the object. The effort is you pushing on that object. So we can use this to calculate efficiency, safety, etc. If we look at this equation, IMA, ideal mechanical advantage, is equal to dE over dr. dE is distance by the effort. So effort distance, or distance of the effort. And dr is distance of resistance, or resistance distance, which is really hard to say. Actual would be what actually happens. You have to do something and take some measurements. So inquiry-based just means that you are doing a little experiment, trying it out. In the real world, there are frictional losses, so it's going to be part of this. And this is also used in efficiency. And here we're going to be looking at forces. So pounds. How many pounds of force did it take? So AMA, here's our equation. Actual mechanical advantage is equal to FR over FE. FR is force of resistance, or magnitude of resistance force. A number and a unit, so many pounds. Over FE, force of effort, or effort force. Think about this for a second. A machine that would have greater mechanical advantage, or I'm sorry, mechanical advantage greater than 1. How about less than 1? All right, a lever. You should know what a lever is. A lever, a rigid bar used to exert a pressure or sustain a weight at one point of its length by the application of a force at a second and turning at a third on a fulcrum. So we see some different types of levers here. The brown triangles represent fulcrums. The arrows represent forces, one being a resistance force, which is the blue arrow, and one being an effort force, you pushing, which is this lightish, greenish, yellowish arrow. So our first type of lever is called a first-class lever. And what a first-class lever has is the fulcrum in between the forces. So fulcrum is located between the effort force and the resistance force in all these situations. It's somewhere in between. Effort and resistance forces are applied to the lever arm in the same direction. So your weight or your resistance is going down. If you want it to go up, you got to push down. It's like a seesaw. It doesn't matter where the fulcrum is. If it's a first-class lever, both arrows, both forces are going to be going down. And this is the only type of lever where you can have a mechanical advantage greater than or less than 1. You're not going to have that with second and third class levers. Our second class lever has the fulcrum on an end and the resistance in the middle. Think of a wheelbarrow. So we've got the fulcrum at one end. Our blue resistance force is in between those, in between the fulcrum and the effort. And now our resistance, our weight, and our effort, what we're putting in, are in opposite directions. In this case, the mechanical advantage is always going to be greater than 1. The third class lever, similar, but now we've switched the forces. The fulcrum's still on the end, but now the effort force is in between. The fulcrum is located at one end of the lever. The effort force is now in between the fulcrum and the resistance, or the weight. So resistance force and effort force are still in opposing directions, and this always has a mechanical advantage less than 1. Think of a tweezers. We also have this idea called a moment. A moment it's like a torque, which we'll talk about that term later, but it's something that makes an object want to turn around a point. In this case, fulcrum. So the turning effect of a force about a point equal to the magnitude of the force times the perpendicular distance from the point to the line of action from the force. And this will make a lot more sense as we look at this. Here's our equation for moment. Moment is equal to distance times force. And that distance, I would write in distance with a little perpendicular sign, so that you remember it's perpendicular distance. Moment and torque are incredibly similar. Moment does not require it to move. Torque means there was movement. Torque is a force that produces or tends to produce rotation or torsion. All right, so to calculate moments, a moment of this lever, we've got our fulcrum, we've got a resistance force, we've got an effort force. We have a distance of 5.5 inches. So calculate the effort moment acting on the lever above. Moment is equal to distance, and it should be a perpendicular distance, perpendicular from the force that we're looking at. So this is at a 90, that's all right, times that force. So we're taking our perpendicular distance, 5.5 inches, times our force, 15 pounds. We get 82.5 inch-pounds. Inch-pounds would be the unit for a moment. When the effort and resistance moments are equal, the lever is in static equilibrium. That'd be like if you were on a seesaw or teeter-totter, depending on what you call it, and the person on the other end is exactly the same weight as you, you could balance both of you off the ground. So static equilibrium, a condition where there are no net external forces acting upon a particle or a rigid body, and the body remains at rest or continues at a constant velocity. So we can use this to our advantage to figure out some things that are missing. Using what you know regarding static equilibrium, calculate the unknown distance from the fulcrum, this triangle, to the resistance force. So if you put a resistance force of 23 2/3 pounds, how far away would it have to be? Think about it this way. If you are going on to the seesaw with the fat kid, are you going to have the fat kid move in toward the middle or out? So we're going to take our effort moment, they're going to have to be equal, because if we're going to be in a static equilibrium, things aren't going to move. In order for them not to move, they got to be equal. So we got to slide in the fat kid a little closer to the middle. 82.5 inch-pounds was our effort moment that we calculated before. So we'll compare it to our resistance moment. Our moment would be a force times a perpendicular distance, although it's got it kind of backwards here, but that's okay. So to get this, we would divide both sides by 36 2/3 pounds, 36 2/3 pounds. The units pounds would then cancel. I guess here it is. So we would cancel pounds. We have that on, it would be 82.5 inch-pounds above 36.66 pounds. So pounds are going to cancel. you get a DR, resistance distance, of 2.25 inches, which should make sense by this picture. If this is 5.5 inches away, this could be 2.25 inches away. Ideal mechanical advantage for a lever. Ideal mechanical advantage for anything is going to be dE over dr, distance of effort, distance of resistance. So this is our mathematical, in a perfect world, representation. So both effort and resistance forces will travel in a circle if unopposed. If I keep pushing down this lever and there's nothing to stop me like the ground, it's going to keep going this way. If I push down here, it's going to want to spin it this way as long as there's nothing to stop it. So you're going to end up with a circle, and that circle is going to be from the radius of that circle is going to be from the fulcrum to the force, the fulcrum to the force. You know that circumference from math classes is 2 pi r. You might have forgotten that, but just a little reminder. This should say pi. There. So our distance would be 2 times pi times the length of the effort arm in this case, if we're trying to figure out how far do you go around. Well, you take this distance times 2 pi. For our resistance arm, how far do you go around? You take this length times 2 pi. So if we put this in this equation, we've got 2 pi times the effort arm length over 2 pi times the resistance arm length. Luckily, the 2 pi's cancel. So we're right back where we started. IMA equals dE over dr. We don't have to worry about circumference. We don't have to overthink it. Actual mechanical advantage, things that actually happen, the ratio of the applied resistance force to the applied effort force. So AMA, actual mechanical advantage, is equal to force of resistance over force of effort. And it looks like we have all the information we need. We've got 2 forces here. Notice this now says 32 pounds, because in reality, we're going to get a different number because of friction or outside forces. So what's the AMA of this particular lever? Well, force of resistance, this blue arrow says 32 pounds. Effort says 16. Pounds cancel. And you would get an answer of 2. And I'm okay with just calling it 2 instead of 2 to 1. They're just comparing it back to 1, 1 being the magic number, but I would just say 2. Notice there are no units. Mechanical advantage is a unitless measure. What is the IMA? Ideal mechanical advantage? That's going to be a little different. Now we're going to look at distances, dE over dr, distance for our effort and distance for our resistance. 5.5 over 2.25 inches will cancel. Now you get 2.44 to 1, or just 2.44. Actual is always going to be less mechanical advantage of in theory. In theory, we should be able to get 2.24, but actually we're not going to quite get there. Why? You tell me. So, as far as why, it's going to have to do with external forces like friction. And this is sort of how we measure how much friction was there. How much efficiency are we losing? You're going to take AMA divided by IMA times 100. So what is the efficiency of the lever on the previous slide? You can go back. You can't really click. You can rewind. If you remember, the AMA was 2. The IMA was 2.44. We put AMA on the top. So AMA 2, or 2.00, over IMA 2.44 times 100. So 82% efficiency. That's actually really, really, really good. No machine is 100% efficient. There's always something that reduces efficiency. Just think of friction in general. There's no such thing as a magical frictionless surface. Wheel and axle, though it may seem different from a lever, is actually very, very, very similar. It's a lever that has gone all the way around in a circle, like we talked about before. It's a lever arm that is fixed to a shaft called an axle. That fixed point is just like a fulcrum. The radius of the wheel is just like a lever. The wheel and axle move together as a simple lever to lift or move an item by rolling. The tricky part might be knowing which is the effort and which is the resistance. Well, it depends on the situation. It is important to know within the wheel and axle system which is applying the effort and the resistance force. Is it the wheel, which is the outside part, or is it the axle, which is the middle part? So a wheel driving an axle example would be like a steering wheel. You are applying force to the outside, and it's driving the inside. Or this lever off a stove or a faucet, where you are applying force on the outside, it's moving the inside. The reverse is also true in your car. Your engine applies the force in the middle, and it causes the outside to turn. Still same thing for IMA, DE over DR. And it's like this going in a circle. These new symbols to some of you, that is diameter, that loop or that zero with a line through it. So it's saying this circle has a diameter of 6 inches, while this circle has a diameter of 20 inches. And we could go back and look at circumference, and it would be 2 pi r or pi times d. Well, dE is pi times the diameter of the effort. So it depends on which is drive and which is driven. So probably the effort in this case is the inner one. And our resistance is probably the outer one. This diameter times pi. Just like before, pi ends up canceling. So we can stick with this equation. Let's not overthink it. So what is the IMA of the wheel above? If the axle is driving the wheel. If the axle is driving the wheel, that means the axle is providing the effort force. And the outside of the wheel is the resistance force, or diameter, I should say. So we take our effort diameter, 6 inches, divided by our resistance diameter, 20 inches, which is 0.3. I'm okay with 0.3, or you can say 0.3 to 1, or 3 to 10, or even 3/10, 3 over 10 in fraction form. What about the reverse situation? What if we are physically turning the outside of the wheel? We're going to spin the outside of the wheel to try to force the axle to turn. So now our 20-inch diameter is our effort, and the 6-inch is the resistance. So flip it. 20-inch effort diameter over 6-inch resistance diameter is 3.33 or 3.33 to 1, or 3 1/3. Oh, no, I don't know. 13 over 3? I think. AMA is what's actually happening with forces. Again, you have to decide which is either decide or be told which is drive and which is driven. So if the wheel is driving the axle, if the effort force is on the wheel, the 70-pound blue force, and the resistance is the axle of 200. So resistance 200 over effort force 70 gives you 2.86 for an AMA, because pounds cancel. Efficiency, well, we'd have to take our AMA from this slide and the IMA, the ideal from the last slide. Percent efficiency equals AMA over IMA times 100. So 2.86 over 3.33 times 100, and we are 85.9% efficient. Still pretty good. A pulley. So here it looks like a crane building some sort of a large structure. Pulley is still similar to a lever. It's still similar to a wheel. It's a lever because it's a wheel, but it's a special wheel with a groove in it. And that groove is helping to either change direction or magnitude of a force, the number, exerted by either a rope or cable that fits into that groove. So ideal stuff, pulley for IMA. So a fixed pulley, a pulley that is just stuck to the ceiling, single pulley. It's got an IMA of 1. If you have a 10-pound resistance, it's going to take, ideally, 10 pounds of effort. All you've done is change the direction. So if all you want to do is change the direction, you use a fixed pulley that's anchored to the ceiling. This is what's called a movable pulley. So it's anchored to the ceiling, but if you pull up on it, the entire pulley would come up with it. If you let go or you let this down, the whole pulley would go down. It's like a second-class lever. It's an ideal mechanical advantage of 2. So now, if you have a 10-pound resistance, you only have to pull up with 5 pounds of force. However, with less force means more distance. You're going to have to pull more rope or more cable. If you have them in combination, like this is what's called a block and tackle, where you have a number of them together. So a fixed and movable pulleys in combination, called a block and tackle, provide mechanical advantage and a change of direction for effort force. If a single rope or cable is threaded through multiple times for a system of pulleys, and you go by this, the pulley IMA is the number of strands opposing the force of the load and the movable pulleys. That's really wordy. It's count the strands except for the one you're pulling on. That's how I do this. So I'd say, well, if I go right across the middle, there's 1, 2, 3, 4, and I'm not counting that one. So I would say IMA of 4. Compound machines, that's just when you've put more than one simple machine. So if one simple machine is used after another, we end up taking those mechanical advantages and multiplying them together. In this case, we've got a lever and a pulley. This is the effort force, so imagine the pulley is somehow fastened to the lever. We've got a weight or a resistance on that lever. We're going to pull up on the pulley. It's going to cause the lever to go up. So to figure out the mechanical advantage of the whole machine, we look at the mechanical advantage of each individual piece and multiply them together. So with our pulley, we can just go off number of strands. 1, 2 strands. I got to think, why does that not work? Let's see. Here I went 4 plus that 1. I think the reason here is we don't count this because you are pulling opposite of the way that it's going to go. It's going to go up. Here you're pulling in the same direction as where this is going to go is up. So we count both strands. I know that's not the best definition. I'm going to have to think of something better. So 2, 1, 2, number of strands. Or we could go by distances. So 2 strands for our pulley system. Our distances for our lever. Our DE, our effort distance, so from our pulley to our fulcrum, is 12 feet. Our distance for our resistance, our mass or weight here to our fulcrum is 4 feet. 12 divided by 4, cancel the feet, so you get 3. 2 times 3 is 6. This has an IMA of 2. This has an IMA of 3. The whole thing together has an IMA of 6. Pulleys in combination. So the force is downward. Maybe that's a better way to say it. Force is downward. We're pulling upward. They're in different directions. We have to count that one. So you can count strands with separate ropes or cables. The output of one pulley system become input of another. This is a compound machine. So pulley on the left. We shouldn't count strands like a block and tackle, though. We should look at each pulley. This pulley looks like a 2. This pulley looks like a 2. This pulley looks like a 2. So each pulley, 2 times 2 times 2, it would be 8. So if we had 80 pounds of force, we'd only have to pull up with 10, but we'd have to pull a greater distance. How much farther? 8 times farther. Actual mechanical advantage is what's actually happening with real weights on there. It is force of resistance over force of effort, just like it always has been. Now we don't have to worry about counting strands, which can be confusing. We're going to take our force of resistance, this weight of 800 pounds. Here's our effort that we're pulling down with, 230. 800 pounds divided by 230 pounds. Pounds cancel. We get 3.48. Counting strands, so here's where we're pulling down. Here's the resistance. It's the same direction, so we don't count this last strand. 1, 2, 3, 4. Our actual is 4. I'm sorry, our ideal was 4. Our actual is 3.48. So knowing that, we can do efficiency. AMA over IMA times 100. 3.48 from that. 4 from the counting of the strands, since they block and tackle. 3.48 times 4, we get 100. Or I'm sorry, 3.8 over 4 times 100, we get 87% for our percent efficiency. Some people think angles don't matter. They do. They matter very much. We'll get later in the year reasons why. It has to do with triangles and trig, but you're spreading out the force. The more parallel, the less you're going to have to do as far as the force. This is the same situation, 80 pounds. Here, we're pulling pretty much straight up. It's split evenly. Here, it's not, because it's like a 40 up here, a 40 up here. We've got a hypotenuse, which is bigger. Math and triangles happen. Yeah, so angles do matter. That pulley is ideal. Ideal is on paper, but really doesn't happen. It'd be the number of strands opposing load only if they are opposite or parallel to that force. So this is down, this is up. We can say ideally it would be 2. Since this is down, but this is an angle, we cannot say that. We would have to do some trigonometry in this case. We won't right now, though. Here is where I got confused with our what to count. So count it if it pulls up. Well, no. Count it if it's in an opposite direction as that resistance. So sometimes it's got to be opposite. Pulley IMA is equal to the number of strands opposing the load. The load is up here actually now. Like it's anchored with 80 pounds of force. You're trying to pull down. That's opposite, so we are going to count these two. Count a strand if it opposes the load, or if the load's movable pulley. Or the load's movable pulley. It could go up, it could go down. That's it.